Guys.
Okay. All right, we are starting and we're slideshow. Current slide.
I got it. Sweet, like this. First come, first served. First come, first served. And chat. Sorry.
Okay, guys, please take a seat and be quiet and follow along in the slides. They're on Moodle, slide number 10. We're talking about signals. Signals are a very interesting concept. Quiet, quiet. The idea is to send a signal from one process to another. Let's say you did a fork and you have now two processes and one knows the IP of another. It knows it's not IP, it's PID, process ID. So you can send a signal to him, which means he sends it's called an interrupt in operating systems. He interrupts him, he stops him in his tracks and he says, listen to this, I've got a message to send you.
Is there a way to pause and stuff just before it down?
No, I'll explain. The name of this function is a curious name. It's called kill. And it doesn't really necessarily kill, it doesn't destroy, it doesn't stop the process. It interrupts the process, it doesn't necessarily end the process. But notice that the first parameter is the PID, that's the process that you want to send the message to. And the next number is an integer. The next parameter is integer, which is the number of the signal that you want to send it. In other words, there are predefined signals, and each one has a number. And you send him, I want to send him number 3, or single number 7, single number 9. So that's what you do, and then he receives the signal. And he stops. It's kind of weird because if you think about it, like, why should a program be able to stop another program just because he knows his ID number? Okay, so the problem with that is that, like, why should somebody be able to stop another process? But there is a solution to that, which is that a process can say, I am not going to listen to a certain interrupt. If I get signal number 7, I'm going to ignore it. We'll talk about that later. If the PID is positive, then it's obviously a positive, it's a real process number. In other words, I'm sending to process number 12. What if I send it to 0? Well, that's kind of weird. Which process am I sending it to if I send it to 0? So in that case, I send it to every process that I could possibly in my group, which means basically every process that I could send it to. Maybe I can't send it to every process in the system, but I send it to all the processes in my group. If I send it as -1, well, there's certainly no process with the PID -1. So then the signal is sent to every process entirely, except for process 1, which is in it. Let's see below. Fine. So you don't send it to init, which is basically the operating system, but you send it to every other process. Well, in our course, we're not going to talk about really sending it to 0 or to -1. We'll send it to a real number. Now there's another question, which is this sig number here, this int signo. So it says like this: if the argument is 0, what if I send to process number 100, or real process, but I send the sig number signal 0? There is no signal 0. So what does that mean? So what happens is the normal error checking is executed, which means we check if the process exists, but no actual signal is sent. So what am I doing? I'm sending a signal, but it's 0 signal, so there's no actual signal. So why would I ever do this? It's a way to determine if the process exists, because it won't actually affect him in any way. But I'll get a reply that he doesn't exist if he didn't exist. I'll get a negative. It will return -1 if the process didn't exist. If we send the process the null signal, but the process doesn't exist, we'll get a -1. We don't have to, and the error number will be set to error searcher. I'm not sure what that stands for. Now, this is not 100% proof that the process that we were thinking about exists or doesn't exist. Because let's say we kill the process. So now it shouldn't exist. Now we send the signal number 0 to that process, we should get back -1. And it's possible that we'll get back not -1, we'll get back that it succeeded. Why is that? Because it could be, even though the process died, his number was recycled and another process has his number now. It's pretty unlikely for that to happen quickly, but it's possible. On success, 0 is returned, on error -1 is returned. So basically, if we get a 0, that means the process exists. Here is another function called raise. What raise does is it sends a signal to yourself. So it's equivalent to kill get PID, where get PID gives me my own ID number. And then I send the signal. So if I do kill get PID, I'm sending it to myself. Same thing as raise. Again, it returns 0 on success. Basically, it would be kind of weird. What if you send 0 to yourself to check if you exist? It's kind of weird. Or presumably you exist if you're sending signal. There's something called an interrupt queue, which reads like this: the operating system maintains a queue for each process of the interrupts that have come through that process and have not yet been handled. This queue could be a FIFO. There could be many interrupts that came one after the other. Ignoring interrupts while handling do we ignore interrupts while handling interrupts or not? In other words, what should we do when we got an interrupt when we're in the middle of handling another interrupt? Kind of like if the doorbell rings and you start talking to the person at the door and then the phone rings. What do? Do you continue talking to the person at the door, or do you stop and say, well, now the phone's ringing, I better go to answer the phone? Or the guy says, well, I'm standing right here, why are you not talking to me? So you got interrupts, so you go to the phone. Now when you finish the phone, you go back to the guy at the door. That's one way. But another way is say, no, I'll ignore phone call as long as I'm in the first interrupt. Anyway, it's not clear. The process can decide. The default is to deal with the newest interrupt first, which means that you would go to the phone call. If the doorbell came first and then the phone rang, you would go to the phone. Which reminds me of a joke. An old lady was once talking to her friend, and the friend wouldn't get off the phone. And so she said, listen, I have to go because the phone's ringing. This is before they were so. So she said, the phone, can't talk anymore. It's a true story. Interrupt table. And it worked. Was it all okay? Fine. The Unix operating system maintains an interrupt or signal table for each process, which means that there's a table of lists of what possible interrupts, well, what of all the interrupts that could possibly come, what should I do? Now, this table lists what action to perform when given a signal, when a given signal is received. Now, there's a default behavior for each signal. In other words, every signal has a default behavior. But we can change that behavior by writing what's called a replacement handler. Or we can even ignore that behavior and just do nothing. Or we can block, which means that it is that we treat it, we put it in a queue and we'll deal with it later. We say, your interrupt, we'll handle it, but not right now. That's called blocking. This queue is usually only big enough for one interrupt, and therefore further interrupts will be lost. Here is the table that kind of clarifies everything that I said. Looks just like this. In signal 1 is called sig hangup. HUP stands for hangup, because it used to be that your computers communicated on a telephone line, and there was a special hangup signal that the telephone could deal with, and if we wanted to tell the other side that I'm hanging up, then we could generate that hangup signal with signal number 1. Now it's called hangup. Sig 2 is sig int, which is signal interrupt. Now what is this exit over here? That's the behavior. What it means is that the default behavior, if I receive signal 2 or 1, is to exit the program. So now we understand why the function is called kill. Because it sends a signal, but look what the signal does. It usually exit. And what about core? Core is also exit. Core is also exit, but it exits by also downloading the current status of the memory of the program. If you remember, in MIPS, you could see all the registers, you can also see the memory values at the bottom. All that information, maybe even including the registers, is like created into a binary file and is stored in a .core file. In other words, it'd be like something .core. And then that core could be read by a core reader if you wanted to. If you wanted to know why your program suddenly got interrupted in the middle, what was it doing when it got interrupted, you have a core file. So that's the standard default behavior of all these signals. It's all to exit. And sometimes to also produce this core file. Now notice that 9 is got a special name, sig kill. Killed. 9 is a special signal. It is intended to really kill the process. And in fact, we'll see that it cannot be overridden. Any other interesting signals here? You see the signal alarm 14. So the alarm clock. When the alarm clock goes off, your program dies. So that's why it's also exit. Here's some more signals. They're also exit, but look, there's a couple special ones here that are not exit. Ignore. All these ignores means they don't die. I don't know exactly what. Oh, here. Sig alarm. Sig. This one's also exit because the word is so long. The column got a little bit screwed up here. But you see, some of them are ignore. Ignore just means that the signal will be received, but I'll continue running. I won't die. Basically, there's two choices. Either I die or I don't die. So signal ignore. If I said signal 18, it will not kill the program. It'll just keep running. It's called sig 18 is actually called child status. It's a special signal that the child sends to the parent when the child finishes. So you understand why it doesn't kill the parent. Because if the child would kill the parent the minute he finished, that would be kind of pointless or bad behavior. Instead, the child just sends a signal that he finished, and the parent continues on. Okay. So now we have our question, which is how to handle signals differently from the default behavior. The default behavior is to do what I just showed you in these tables. How can we change that? So we have a special function called signal. This is very confusing. Kill sends signal. Signal does not send signal. Right. Signal changes the signal behavior for a given process.
We have to use that. So.
You have to use it for the shell because we wanted to have what?
We had to.
You had to. Well, like I said, you did the labs.
Because we're the control C behavior.
Right.
That's basically like that.
So you figured. So now I'm explaining to you what you already learned. But I'm explaining to you thoroughly. Maybe you.
No, that's fine.
Maybe you understood it partially. Anyway, signal system call allows me to change why for the control C, because when you do a control C in the shell, this is how your shell should have worked. When you hit this control C in the shell, it should send now, instead of killing your shell, it should send the signal to whichever process the shell was running, which it knows the number of that process, because when it created that process by fork, it got back the ID of that process. So it should sort of forward along the signal. That's what you did, yeah? Anyway, the signal system call allows me to change what my process does when it receives a given signal. Signal installs a new signal handle for the signal with sig number. In other words, I specify sig number, which signal I want to override, and then I give it a signal handler. It can the signal handler can also be sent to sig ignore, which means I don't want to do anything. I just want to ignore that signal. It can also be sent to sig DFL, which stands for default, which means put it back the way it used to be. Put it back to the default behavior according to the table. Upon arrival of a signal with the number sig number, the following happens. If the corresponding handler is set to sig ignore, then obviously it's ignored. If the handler is set to default, then the default action is set. And if it's set to a handler, we go to the handler. If the handler is set to a function handler, then sig handler is called with the argument sig number. In other words, the function gets exactly one parameter with the sig number. We'll see how to do that in the next slide. But first, before we do that, a couple of side points. The signals sig kill and sig stop cannot be changed or blocked or ignored. Why is that? We want to be able to give the operating system the ability to kill any process. If a process would be able to say, I'm going to ignore every signal that there is, then how could we ever kill the process? Using a signal handler function for a signal call is called trapping or catching the signal. The signal function returns the previous values of the signal handler. Oh. In other words, or sig error on error. So the signal function can be used to like put back the previous handler. If I keep going from one handler to the next, I can find out the previous one. Okay, here's a function. So look what I do here. Look at this beautiful little program here. The main thing I do in this program, what's the main thing I do in this program? Aside from printing hello. What's the other weird thing that I do in this program, or unusual thing that you shouldn't do in your program?
Divide by 0.
Exactly, I divide it by 0. When I divide by 0, first of all, this will pass. If I would write it 7 divided by 0, it wouldn't compile. But in the way I wrote it this way, it'll compile, but it'll give me a runtime error. That error will actually generate a signal. Which signal will it generate? It will generate the FPE signal. What does FPE stand for? Floating point exception. Because when you divide by 0, you get a floating point exception. So I generated that signal without sending the signal, just by dividing by 0. But before I generated the signal, I wrote this command signal, which means when I get sig FPE, which of course I'm going to get over here, instead of doing what you normally do, which is what? Let's go back. Sig FPE core. Core means die. Instead of dying, do the function sig FPE. Well, that function is in here. Notice that it takes exactly one parameter, it has to, and that's the sig number, which will be 8 in this case. And it'll print, you divided by 0, didn't you? And that's it. Well, then it'll do this funny thing called raise sig alarm, which means it'll send itself the alarm signal, which also kills it. So I actually killed myself here. So first I printed you divided by 0, and then I died. So I sort of snuck in a printout before I died instead of just dying. Here's another example with the sig int, where I'm going to take, where is it? Here, sig interrupt is the name of the function. But here I do signal sig int. If sig int should occur, do the function sig int. Now control C will normally send me a sig int and kill my program. But now if I do the control C, it'll run this function, sig interrupt, and it'll write receive sig int, but I ain't quitting, and return. It won't die. So now I made an infinite loop, which in general you shouldn't make an infinite loop because unless you have a pause or something to slow you down. This pause is going to slow me down. I'm going to do a loop and then immediately stop. And I'm waiting. Pause is a special function which waits for any signal. And it's going to sit there. And the minute the signal, say I could have done without the pause. I could have actually done the same program without the pause. Then what it would do, it would run like mad, this loop, millions and millions of times. Then when I eventually did a control C, it would stop and go receive sig int and quit, and then go back to the loop. And it would just, the CPU would be very, very busy. For what I call like burning the CPU. I would be busy making the CPU very busy. So instead of doing that, I put a pause here. And now it'll only run once in a loop, and it'll just sit there waiting until I hit control C, and it'll say receive sig int, but I ain't quitting because I overrode it. And this will work every time. Now, theoretically, we could imagine a case where signal worked differently. In fact, it used to work differently. It used to work that only the first time would it print I ain't quitting, and the second time it would revert to its default behavior. Nowadays, signal doesn't do that, but originally sig int, or traditionally, signal just works one time. If it worked one time, how could I make it work many times anyway? Simply, I could put this if inside the loop. Anyone think of another idea? If I put this inside the loop, then it would run these two lines inside the loop, then every time I'd reset it, even if it only worked once. Another possibility is to put these two lines inside the function itself here. If I put them inside the function, then even though then it got reset, then I reset it again back to this thing. So I could internally inside this interrupt function set it back in. Anyway, that's the old ways to work. We'll talk about that more actually. Demonstrate using a parameter of handling. So we set as a parameter, let's prove that it works. So here's sig user sig number. And here what I did is I said for either sig user 1 or sig user 2, sig user 1 and 2 are what values? 16 and 17. And they both exit. So what am I doing with them? Instead of exiting, I'm doing the program sig user, and then in this sig user, I'm going to check what's the number that I got. The number that I got will be either 16 or 17. If sig number that I got is equal to sig user 1, which is 17 or 16, then print receive sig user 1. Else, if it's 17, then print receive sig user 2. And that's it. So you just see that I'm using the sig user number to differentiate. I could theoretically write one function for all of my handling and always go to it and then just check how I got here. Right? And just check how did I get here. Okay, next. Well, here's a complicated example. That was simple. Here's a complicated example with an alarm. Now, what I do with this alarm is an alarm basically sets a certain time. So when let's say I do like here, where is it? Here, alarm end seconds. So if I just write alarm 10, then after 10 seconds, I will send a signal to myself called the alarm signal, which will then kill me. So it's kind of like an alarm, but it doesn't. What it does is it kills me. Now I want to do it a little bit differently. I say like this: if sig alarm. So first thing I do. First thing here, first I declare a variable unslept. I make my loop, and I say go to sleep. Well, I just print that go to sleep. And I do my sleep. I run the function with 2. And what happens when I run the function with 2? Here's my sleep. The first thing my sleep does is he says, well, wait a second, before I set the alarm, I'm going to make that the alarm goes to a function called sig alarm, which does nothing, returns, but won't kill me. So then I will get an alarm message, but I won't die. Now I set the alarm to whatever number of seconds I got over here, which in this case is 2. And then instead of normally I would do something. I would start writing my program and I'm setting an alarm and I'll stop after 2 and until I get that signal. Instead, I did nothing. I just do a pause. And then basically I'm going to sit there for 2 seconds. And then all of a sudden the alarm is going to happen. The pause is going to get the signal. It's going to go up and do nothing. The pause will now break because the pause only waited for one signal. It got the signal. So when it returns, it'll return to the next line and it'll return whatever value alarm at 0 gives it. And then that value will be.
What is alarm 0?
I'll explain. And that value will be unslept, and then I print unslept. Now, what is this value that I'm returning? Well, when you run alarm with 0, if you think about it, it's kind of meaningless. Right. If you say alarm right now, no time. So what's the point of that? Just send the alarm signal to yourself. So what it does is it tells you how much time was left on the alarm that you previously set.
Okay.
So if I would run it, let's say, right away after this, then it'll probably give me back like 2 seconds. But this way, it's going to give me back 0. Because I waited the full 2 seconds.
Right, so what's the point?
It's to find out how much of, if I woke up early.
Like an alarm came from somewhere else?
Maybe, yeah,
Okay.
exactly, if an alarm came from somewhere else. Or if I set myself another alarm, basically it's I think if we look at the alarm, let's actually, let me. Oh, wrong thing.
What's
yes.
going on? So,
I want to print that and again. I just want to check for let's look at the manual page. Man alarm. I always am impressed with this. You can just type man alarm and it knows what you mean. See, here, here's the first thing here. is the Linux manual page. If seconds is 0, any pending alarm is canceled. So that's the first thing that it does. If I would write sig alarm, if I write alarm 2 and then do 0, it would immediately cancel the other one. Now, what is return? Return value. Alarm returns the number of seconds remaining until any previously scheduled alarm was due to be delivered. So whenever I set a new alarm, if I have one alarm and then I set another alarm, it's going to return to me how much was left on the previous alarm.
Okay.
That's what we said. Just to clarify. Slideshow from current. Slideshow from current. Okay, so we saw that this complicated program with alarm. Where were we?
Next one.
Next, okay, yeah. An example demonstrating sending a signal to a child process. So here's already a little bit more interesting, maybe. I don't know what's interesting, not anymore, but I thought this was interesting at one point. A child receives, so what do we do here? Sig user is a function. This is the function child receives sig user one. I am PID dot number sign, number. And then get PID. So the whatever value get PID will be put where the dollar, where the percent D is, and it'll say I am PID, whatever number it is. And that's it. Essentially, it's like saying return. So this will not kill the program. Now what I do is I say like sig user one, sig user. So if I get sig user one, go to this function called sig user. And assuming that this worked, p error, and here's by the way use of p error, where I print 2, not 1, but 2, standard error. And I print this message. I can't catch the signal. Now I do a fork. Now the child ID by the father will be the number of the child. By the child, it'll be 0. So if child ID equals 0, then I'm a child process, child is running, infinite loop with a pause. So I'm just sitting there doing nothing. Now the father says sleep for 4. This is a bad solution to a race condition, right? Because if I wait 4 seconds, presumably the child will have already started this loop. Of course, that's not a guarantee. Notice that that's just a clumsy solution to race conditions, because you don't know that 4 seconds is enough. Maybe you need 10 seconds. Whatever number you write there, you can't be sure. But anyway, let's assume it works. Now the child, I send a kill to the child. Now, by the way, it's very important to notice that this was done before the fork, which means that a child inherits the table, the signal table of the father. The father made this, and then he made a child. The child got this change. So when I send to the child sig user 1, he's gonna get it, and he's gonna print child receive sig user 1 I am, and then it'll print his PID. And of course I sent it to child 1 because by the father, child 1 is his value. I know his number. Then I send him another signal, which is sig kill. Now, number 9, this is sig kill, which is number 9, which is impossible to catch. So that means the child will for sure die here. And child will be a zombie for a few billionths of a second here, because I killed him and I didn't yet do wait. But then the next line I do a wait. So I read the child.
I heard that.
And then I say, what is this? Here, Nachum, what does this do? Kill child 1, 0. Remember what did I do when I send 0 in this kill signal?
Everyone in your group?
What?
Everyone in the group?
No, that's if this number is 0.
Oh.
If this number is 0, I'm sending a specific child the signal 0. So 0 doesn't send him anything. It just checks if he's alive. So basically, and I killed him and then I reaped him. Now I'm checking if he's alive. Error value should be -1, that he's not there. I don't know what this other line is there. This other line is printed. Okay, fine. Slideshow from current slide. Okay, so that's our nice example of sending a parent sending to a child a signal. This is relevant for the Targil that you already hinted in, which is the shell, because when you did Control C, then the parent had to send the child this signal.
Yep.
Important note: What should the operating system do if a process receives an interrupt while it is in the middle of handling a different interrupt? Oh no, the same interrupt. On some operating system, it ignores or blocks the interrupt until it has finished the first interrupt. In other words, why if I'm already doing a certain procedure, and then you interrupt me and you tell me to do the same procedure again, well, I'm already doing it, so I should just ignore it. Some versions of Linux do not do this. Instead, they immediately handle the second one. But instead of doing the interrupt function handler, they do the default behavior of the interrupt. In other words, it's sort of good. If you hit like Control C the first time, it'll do the regular. But if you do quick ones, then the second one will do the normal behavior and kill it. This can be a problem if your program is not properly synchronous. You might not want that. This leads to the desire to be able to block or mask interrupts during the handling of the interrupt. In other words, presumably when I'm doing an interrupt, I should say I'm doing a priority activity now. Don't interrupt me. So I should be able to block all signals if I want while I'm doing a signal handle. How do we do that? There is actually a sigmask function. But wait, before I do that, I'm going to explain how to do it a different way. Traditional behavior of signal. So traditionally, the signal function sets the handler only for the first occurrence.
So you're talking about for the old.
That's what I said, the old system, traditional. All subsequent occurrences of the signal revert to the default. If one wished in the old days to handle all following occurrences of the signal in the same way, one could redefine the signal, in other words, reset the handler by calling signal in the handler itself. We said a problem can arise. What if the interrupt occurs before the handler has time to reset itself to the handler? Then that would this is a classic race condition. More about this later. Now, this next solution is not a good solution because it relies on me getting to do at least one line before I get the next signal. So we have a function. Oh, so first of all, we have a function called sigprocmask, which I said exists for the purpose of blocking signals. And we also have a race condition here. Because let's say I'm the first line of my signal handle, I start blocking all other signals. But what if I get a signal before I made the blocking? I have a race condition. But I'm just telling you the existence of this function. Sigprocmask is used to fetch and or change signal masking of the calling the calling thread. The signal mask is the set of signals whose delivery is currently blocked for the call. In other words, I can block a signal. Blocking, what is blocking? What's the difference between blocking and ignoring? Blocking is that I throw it away. I totally get rid of it. Ignoring means I throw it away. Blocking means I just wait. I do it later. So here's how you run this function. There's a function sigprocmask, and there's the how parameter, the set parameter, and the old set. Basically, the old set is, we'll explain the old set last, but the how is basically what I want to do. The set is on whom I want to do it. So, an old set is a place for me to capture the previous value. So, for example, if old set is non-null, it's a null pointer, then I won't get anything. But if it's not a null pointer, it's a regular pointer. It's a set pointer, let's say, some kind of set pointer. It's a sig set. It's a sig set type pointer. The previous value of the sigmask is stored in the old set, useful if we want to return to the previous state. What are the possible behaviors that I can put in the how? Well, it could be block, it could be unblock, and it could be set mask. Block means block these signals, unblock. Remember, block means add these signals to the block list. There could be 3 already there, and I want to block 2 more. I can add them with block. Unblock means remove these from the list. And set mask means redefine the mask as follows. So again, I would write how, let's say block, and then here I make a set of signals that I want to block. But so the set would be, all the signal numbers that I want to block. But this method is no good because of what I said. It doesn't actually help solve our problem because we'll have a race condition. So there's a more complicated function called sigaction, which really everybody uses nowadays, and even for 20 years everybody uses.
Okay.
But signal is theoretically, if you're teaching this course, if you're teaching a course in like operating systems, it's just enough to teach signal, because that's the basic idea. Sig action is just a little more complicated way of doing the same thing. We can use a new function that by default keeps itself as the handler forever until you reset it back to the original handler. So we don't, thus there's no need to redefine the signal handler in the handler itself. And in fact, I think that signal actually just calls sig action, and that's why it works that way nowadays. Of course, it's only by default. You could still tell in sig action, you could still say, no, I want this to be chad pami, I want this to happen one time. This function will also allow you to mask, no, this also will mask the same interrupt during the handling. In other words, if I've set the signal, let's say signal number 7 to go to this function, then automatically it'll also mask if signal number 7 occurs again while I'm handling. So that just does by default. And we can even add more signals that we want to mask during the signal handling of the function. We can also allow, it also allows you to add more. And it's not, there's no race condition because sig action is atomic. It happens as one action. Obviously, this function is going to have a lot more parameters. We're going to set all kinds of stuff as parameters, and then it does it as one action. Nowadays, signal has been rewritten to essentially be a call to sig action, so that signal will also now remain set for future interrupts, and presumably also block itself. Okay, example using sig action. So let's see how you use it. Here is an example showing the use of sig action to set a new signal handler for sig in. Note the use of the structure sig action. Yes, it has the same name as the function. This drives me crazy.
What structure?
There's a function we're going to use. You'll see in the next slide. We have a function called sig action, and it uses a structure called sig action.
Okay.
A structure is a class without functions.
Yeah.
In C, we precede a declaration of a structure with the word struct. This structure has many, even a declaration, not a definition, a declaration. This structure has many attributes, and we will use only some of them. Other attributes will set to 0. So here we go. Here, let's just go straight to the line. Here we see it only has 3 parameters, except that this is the sig int that I want to
Sasa.
just a second. SA stands for sig action. Sig action, sig int. Sig int is the signal I want to reassign. Null we can ignore. What is SA? Well, SA is a struct. Notice that SA is defined. Struct, sig action, SA. So we have this instance of the structure sig action. It has all kinds of parameters in it. I'm not concerned with what their content is, except for some of them. So what can I do? Here's memset. Memset allows me to declare all the values in a structure or in anything, in an array, to be any value I want. So I take the address of SA, which now has garbage in it, and I put in 0. And I give how many zeros do I want to put there? And this is like a point at the beginning of SA. And I say all of SA according to the size of SA. So I set it all to 0, which is essentially saying I don't want there to be garbage there, but I also don't want to set anything. Now that I've set it to 0, I can take the handler part of it, because remember this SA has all kinds of parts. I can take the handler part and set it to be a pointer to my handler, which is written above. And now I can simply run this loop 2 times and sleep. And notice what I do here. I make a global counter. This counter is global so that and it's also atomic. I don't know if you remember, we talked about it's an operating system, it's an atomic type. It means that it can be changed, but it can't be changed by 2 different people at the same time.
I'm using a service right now to change it. If 2 people are on different computers and it updates.
Well, that's what it should do.
It's not good. No, it's not.
Oh,
It doesn't have race conditions or it doesn't.
it's ACID. You want ACID transactions. You know ACID transactions?
It's of course. And like. Your best.
ACID is an acronym. Look it up. ACID transactions.
You know that's this?
Huh?
You know that's this?
Not master. It's a master.
What?
Acid transactions.
Yes.
Acid reflux.
No.
Atomicity, consistency, isolation and durability.
That's it.
Yeah.
You want atomicity,
Atomicity.
you want it to be atomic.
It's atomic.
Atomic.
Hiroshima and Nagasaki.
No, that's.
Yo.
Okay,
What's the?
so what do we do here? We basically did the same thing, but now we didn't actually set any masks notes. We just set the handler, notice the handler could also be set to sig ignore or sig default. But what, and then we put a null here, we don't care what the previous values were, for some reason. Okay. And then we go to a loop, and if the guy hits Control C 6 times, it's gonna go here and sig counter will go up by 6, and then I'll print 6 times. Okay, example 2. Now we're gonna capture the old definition, set the handle back to what it was before. So look what we do here. We again have our SA, sig action type. And we put the handler in, but here we actually put the old action in, because we have, what is old action defined as? Old action
No idea.
is global, it's also the same type, we made it global. Why do we make it global? Because we want to use it in this function too. And we can't pass it as a parameter, because the only parameter you can pass is the number of the signal. So this parameter here, signal number. But I want to use sig old action, so what did I do here? I changed it to sig int. I changed sig int to use SA, which has a handler, which is defined as this handler. Then I do a sleep for 20 seconds, and presumably the guy hit Control C in that 20 seconds. Then he goes up here, sig count goes up by 1. In handler is printed discrete. We sleep for 3 seconds. That's just so that I can test if I can do another Control C. And then sig action, sig int. What am I doing? I'm reversing it. I'm taking sig int and I'm putting old action here. Old action is what I defined over here. I'm putting it back, reverting it back to what it was. Remember I said that if I want it to only happen once, I could do it that way. Now it only happened once, and I woke up sig int. Sig woke up and sig int was reset.
Okay, so now do.
Now if I do another, came back, if I do another sleep here, I do sleep 20. In that sleep 20, if I hit it, it should actually kill it. You see? I'm just sort of proving the behavior. Now we have the final piece of the pie, which is how do you mask other signals while I'm in a given signal?
Mask needs to postpone here,
Well, yeah, means to postpone, yes.
like.
As we said, by running sig action instead of signal, we block further occurrence of the same one. But we can also add more signals to be asked during the handling. Do this with sig add set. In other words, we add to the set of things that we block. A signal, a particular signal. We can also use sig empty set to remove all signals except the signal being handled. After the structure is defined to our liking, we run the sig action function and apply it. By putting all these parameters in one system call, this says we can perform it atomically. So here's an example where, look what I do. Again, I have the old action. I use the old action here, just like we did before. But before I do a mem set like I did before, I set the handler and I do one more thing. I sig add set to the, this time not to the SA handler, but to the SA mask. I add to it the signal sig user.
Spark has an app too.
Exactly. So SA instruct has several fields which will just the ones that I show you.
Yeah.
So it has a mask field, and then when I do this single action, sig action, it does both. It changes the signal of sig int to be whatever is defined as the handler in SA, and it also masks sig user at 1. That's it for that lecture. Let's do the next lecture. You guys are so attentive that I think.
You lost it?
Is this about 12? Is there 12?
It's Pete Fritz. We're done with the chorus.
No, we're not.
We have 11,
Here's another one.
I thought there was 12. Let me see.
Yeah, right here. Beep.
P-thread's 11,
Yeah,
yeah,
there's
I
another.
was wondering if there's another, I was
Oh.
thinking one ahead.
I was trying to talk about. It's a bit of a big, you know.
Alright, P-thread's a big topic, but good to start. Did we do make files? Did I show you how to make files?
Bless you.
We should have. We did make files, thank you. No, wow, I can't see it because this stupid thing is here. Yeah. Here, 11, okay. Slideshow. Yes, from current slide. Okay, lecture 11. We could do some more topics, actually. I have some more topics, maybe I'll add some.
Do random stuff.
No, I have more slides that I prepared, for some years, I do more stuff.
Okay.
Depending, like this is the minimum, and then I have some extra stuff.
Can we go over what the final questions are?
Not now,
How many labs do we need to turn in?
all, it says,
6?
the last two, you only do one of them. Okay, POSIX threads. POSIX is an organization that defines standards for how to do things. Up to now, we've talked about making forks. Forks is to have new processes. But we might want to have threads. Did you guys do thread programming in like Windows?
We did it in
In
Windows and
Java.
Java systems.
And an operating system, you did it, oh,
With you, we did.
with me, but we actually programmed it, or we just?
Yeah,
We did a mini project.
We did a mini project?
We did. No, we did Java.
Oh, a mini project.
Java, we did multi-threading.
Yeah, that was fake though, man.
Java, yeah, Java threads are in the Java world, they're not really in the operating system.
That's rude.
So fake.
They're called, they're user threads, they're not system, they're kernel threads.
Yeah, nice try.
In the Unix environment, a thread exists within a process and uses the process resources. It has its own independent flow of control as long as its parent process exists and the user's operating system may share process resources with other threads that act equally independently. Dies if the parent process dies. Okay. P-thread attributes. A thread can possess an independent flow of control and be schedulable because it maintains its own stack, registers, scheduling properties, set of pending and block signals, thread specific data. Managing threads requires fewer resources than managing processes. Pthread create runs faster than fork. All threads within a process share the same address space. Inter-thread communication is more efficient, easier to use than inter-process communication. Pthread library. The subroutine which comprise the Pthread API can be informally grouped into three major classes. Thread management. The first class of functions work directly on threads. Mutexes, so there's thread management, there's three sets of functions. The thread management functions, the mutex functions, and the condition variable functions. Mutexes are for mutual exclusion, and conditions third class is for communication between threads. How to compile. First of all, if you're compiling three threads in a Unix environment, you have to use the -L pthread extension in your compilation. Initially, your main program comprises a single default thread. All other threads must be declared using the pthread create function. Here you see pthread create. It has a bunch of parameters. We'll go through them one by one. How many parameters do you see? There's the pthread type, or is it something of pthread type, which is the thread itself. There's the attributes. There's the routine that you want to run, and the argument. It creates a new thread, makes it executable. Typically, the threads are first created from within the main inside a single process. Once created, threads are peers and may create other threads. So a thread can create another thread, and it's not a you see, it's different a little bit. They're peers. If a thread creates another thread, they're all brothers. They're not considered grandchildren. The pthread create function returns the new thread ID via the thread argument. That's this argument that we see. Via the thread argument over here. The thread that I give it, I get the ID inside of this pthread type, this thread ID. The caller can use the thread ID to perform various operations on the thread. This ID should be checked to ensure that the thread is successfully created. The attribute parameter is used to set the attributes. You can specify thread attributes, or an attribute object, or null for the default values. We're going to just use null. Start routine is this C function that the thread will execute. A single argument is passed to the start routine via argument, which is the last parameter. Must be passed by a reference as a pointer of type void, which means when you have a void pointer, you can give it any kind of pointer. On success, 0 is returned, on error, non-zero error. 3 ways of terminating a thread. A thread returns from its starting routine, so you have a return function. The thread makes a call to the 3pthread exit function. And the entire process is terminated due to a call to exec or exit. A finishing question. If a thread runs exec L or exec P, then the whole process will finish. So here's an example of code where I create 3 threads, and there's a function called hello world, and that's the function the threads are going to run. So what do? I run pthread create, and I run it in a loop 3 times, where I run each time with a different thread in the array threads that I made. And I give it null and the function and a pointer t. What is t? Well, t starts off at 0, becomes 1, 2, and 3. Then t is passed as index, which is of type void, and then I print it as a number. It's a little bit ugly, but it works. Why is it ugly? Because I didn't do any explicit casting. Should really do explicit casting. Pthread exit. Now, in this case, I did pthread exit. Now, if I had done regular exit, the first thread to hit the regular exit would have ended the whole program. By doing pthread exit, what I say is let the thread exit, but do not kill the process. The main thread will stop. In other words, whatever thread that runs pthread exit will stop and will remain in a zombie or spunk state until all other threads exit. It will sort of be hanging around doing nothing. If you are using pthread exit in the main thread, you cannot get the return status of other threads. You cannot do cleanup for other threads. As if the main thread is pthread exit, the main thread is gone. And there's sort of nobody who knows about the existence of the other threads. Each thread is now running, but there's nobody to clean up because each thread doesn't know how many other threads there are. It is better to detach threads with pthread detach so that thread resources are automatically released on thread termination. In other words, there won't be zombies. Shared resources will not be released until all the threads that share them exit. And there's also a pthread join, which blocks the calling thread until the specific thread terminates. So as I can wait, it's essentially waiting for a thread. If I create a bunch of threads and now I want to wait for them all to finish, I can join them all. The program is able to attain the target thread's termination return status if specified through pthread exit and then getting the status. So here you see, this is the example continued. If you went back to the example, I created the threads and instead of just doing pthread exit, now I'm going to, before that line, I'm going to do another loop where I wait essentially for each thread. I do pthread join on each thread in a loop. Now RC should be 0 if it succeeds. So if I ever get not a 0, I'm gonna stop, close the program. And if I didn't, if they all succeeded, then I can write completed join with thread. Okay. What about synchronization? Well, here's an example of synchronization where it's obvious that I need synchronization because if I read the balance as 1,000, he reads the balance as 1,000, I deposit 200 and he deposits 200, and I'm gonna update it from 1,000 to 1,200, and here also, but it is 1,400. The mutex variables are one of the primary means of implementing thread synchronization. A mutex allows me to lock shared data. And the basic concept of mutex as used in pthreads is that only one thread can lock or own a mutex variable at any given time. All right, I'm gonna stop here. We'll continue next time.